Okay, so let us first discuss now why do I get parabolic shape of the free energy curve. We know that G is equal to H minus Ts, right. So therefore, change of free energy can be written as delta H minus T delta S. Now delta H can be easily obtained by thermodynamical means using the Cp of the system. We know the heat capacity of system can be used to calculate delta H, but for a solution containing more than one component, delta S is also a function of compositions. So that needs to be measured or obtained using the rules and regulations of entropy. How do I go about it? We know that S or entropy as per Boltzmann formulation is given as K ln W. K is Boltzmann constant and K is also can be written as R by N0, where R is the universal gas constant, N0 is the Avogadro number, and W is nothing but number of arrangements, probable arrangements possible in the system. Suppose if I have 4 balls, 3A and 1B, and I have 4 different positions to keep these balls. How many number of ways I can arrange them? There are only 4 different ways I can arrange them. You can do these games with yourself. You buy 4 different balls, 3 of green color and 1 red, and then try to put it in a box containing 4 different places. You will find there are only 4 different ways to arranging that. There will be no other ways of arranging that, correct. Similarly, if you have 2A and 2B, or 2 red and 2 green balls, you will have 6 different ways of arranging them. So this W means that, W means how many number of ways of arranging this system. So now suppose if I have n, capital N number of A atoms, this is number of A type atoms, A atoms, and n minus 1, n minus small n number of B atoms, and I want to arrange them in a lattice containing n sides. So what will be the probability? Probability will be n factorial divided by n minus n factorial and n factorial. How do I get this number? This is basically from permutation and combination. That is what you get. I do not have time to discuss in detail of that. This is simply by permutation and combination you can get this. So therefore, this is the number of ways arranging n A atoms, n minus small n B atoms in a lattice containing n sides. Now question is this, if I have to calculate delta S of a system, let me just do it there, delta S of a system, suppose delta S of a system, so then I will write down S AB minus SA minus SP. Why? Because this is delta S is the difference of the entropy of the system containing A and B atoms minus entropy of the system containing only A atoms minus entropy of the system containing only B atoms. These two must be subtracted because they are when there is only A only B, and there is only A only B means there is only A or B types of atom present. Here only A type, here only B types, but here you have mixture of both of them. So now I can write down like this, K ln WAB, K I can take common, ln WA, ln WB. Okay. So that means I can write down K ln WAB. Why? Because WA is 1. If I have only A type of atoms, arranging A type of atoms in a number of sites, suppose n capital N number of sites is 1, there is only one probability. You cannot put, you can only put one A type atom, there is no option. Similarly for B also. So this log of 1 is 0, log of 1 is 0, this becomes cancelled. So that means this one is like n capital N minus, okay, and I can expand this and using Stirling approximation. What is Stirling approximation? This one can be written like this, log of n factorial minus log of n minus 1 factorial minus like this, and we know the Stirling approximation is I write here Stirling's approximation is this, that n log n log of n factorial is equal to n log n minus n log n minus n. This is what is Stirling's approximation. So by the way, if you apply this, finally what you will get is k n log n minus n log of n minus n. Okay, you will get this, and if I take away this one, then what will I get? I will get delta S is equal to minus k n by n plus n log of n divided by n plus n plus, this will be plus, sorry, plus n minus n divided by n, okay, yes, log of n minus n divided by n. And we can define this as a mole fraction of xa. So this is equal to r minus r, because k into n0 is r. So this n is also Avogadro number of molecules. So this becomes xa ln xa plus xp ln xp. Okay, that's what we get. So total entropy change is this. So now this has to be replaced here. If you see here, if I replace this one, this is xa ln xa, xp ln xp, or we can write down minus r xa ln xa, ln is log, plus 1 minus xa, because xp is 1 minus xa, 1 minus xa. So you can clearly see this is equation of parabola. This is nothing but equation of parabola, because log of xa can be expanded. So if you expand it, it will be xa multiple x-ray, it will be xa square. So this is nothing but equation of parabola. Similarly, 1 minus xa will be multiplied by 1 minus xa if you expand log, so that will also be xa square. So that's why actually it becomes a parabola. So all this curve, that's why you see here, is nothing but a parabola. This is the parabola. This is why it is looking like this, otherwise not. So let me now move ahead with my first derivation. This is I just wanted to clarify you why you did get a parabola. Otherwise in future you will say, sir, you have shown this parabola but you have never explained why it is parabola. So let me just now go ahead with the phase rule derivation here. So we know that G is a function of temperature, pressure, and your number of moles of A, number of moles of B, and I have shown you that dg can be written as, or dg prime rather, because G has to be divided by number of moles. This can be written as V dp minus S dt plus mu A xa, mu A dxa plus mu B, sorry, dxa should not be written here because Na I have written, so this will be dNa and mu B dNb. Now let us assume a situation in which there are two phases, alpha and beta. Okay, I have shown you lot of example of iron and other systems, and alpha contains Na alpha of A and Nb atoms of B. Similarly, beta contains Na atoms of beta, Na atoms, and Nb atoms of beta. Okay, these are the number of atoms present. Now suppose there is a transformation from alpha to beta, or rather let us suppose some atoms of beta is getting transported to alpha during a transformation at a constant temperature pressure. So therefore what is the change of phi and g? So let us first write down phi and g expression for alpha. This will be all alpha. I have to put alpha only everywhere. superscript. Similarly, beta sorry, you can close your eyes and write down only beta superscript and get that. These are the free energy changes when you have such a system like that. At constant temperature and pressure, these two variables will be vanished because temperature, pressure, dt and dp are not changing. So let us now do this calculation. If I have transporting, suppose if there is a transport of Na moles of A from beta to alpha, what will be the change of free energy? Change of free energy will be very easily written, that change of free energy is for alpha will be mu A alpha, mu A alpha dNA alpha, because Na number of molecules are changing, not Na, it has to be dNA, otherwise you will be confused. The dNA number of molecules are changing, so alpha will be, this is the change of energy, because there is a change of B. So therefore only this part will change. This we have already assumed the pressure and temperature constant. So dP is 0, dt is 0, dNB is also 0, but there is no B molecules getting transported from beta to alpha, only A molecules transported. Similarly, this is for G prime alpha. Similarly, for G prime beta will be mu B will not be there, mu B alpha, नहीं होगा, mu B beta, yes, mu B beta, oh I mistake, this will be A, yes, mu A beta dNA beta, correct, because only A molecules are transporting, so these NB are not changing at all, I have assumed that. So now what is the total change of free energy? Total change of free energy is addition of these two, Gg total is addition of these two, Dg prime alpha plus Dg prime beta. So that is nothing but summation of these two, mu A alpha dNA alpha plus mu A beta dNA beta. Okay. So for any system to be at equilibrium, the total free energy change should be constant. So for total, for equilibrium dg total or dg prime should be 0. If I have to make 0, this whole thing is 0, that is mu A alpha dNA A alpha plus mu A beta into dNA beta 0. As you know that I have transported DNA molecules from beta to alpha. So therefore, if I transport that, therefore DNA alpha must be equal to minus of DNA beta, because the whatever is molecule I am transporting from beta only getting added to alpha. So there is a change this way. So that means I can write down mu A alpha minus mu A beta multiplied by DNA alpha is equal to 0. As you cannot have DNA alpha to be 0 because this is a mass cannot become 0. So since I can write down DNA alpha cannot become 0, mu A alpha equal to mu A beta. This is a very important condition in thermodynamics. So you can see here, if two phases are to be at equilibrium at constant temperature pressure, the chemical potential of A in both the phases must be equal. Chemical potential of A in alpha must be equal to chemical potential of A in beta. Remember this, I have not changed the subscript, I have only changed the superscript. Similarly, chemical potential of B in alpha must be equal to chemical potential of B in beta. These conditions must be satisfied. If they are not satisfied, you cannot really talk about equilibrium conditions in solutions. This I just want to derive and show you how using physical metallurgy, thermodynamic principles like total free energy change 0, I can derive this expression and show you that. So now question is this, how can I use this? This is what is shown in this picture, right? Let us do that analysis. You can clearly see that if I go back, this is my free energy curve, free energy versus composition, composition suppose XB, composition is increasing this way, this is my pure A end, pure B end, correct. So pure A end will have free energy equal to mu A 0, pure B will have free energy equal to mu B 0, that we have already defined, and free energy will be like this kind of shapes. I have already discussed you why this kind of shapes will be there. So if I now wanted to know free energy at a particular composition X, that is what is Gx, then I can just draw a tangent to the curve, okay, and this tangent will be passing through this dotted line, this dotted point will be tangent to this curve. So in that case these two ends will give you the chemical potential of A and chemical potential of B, okay. So now if we consider this is for alpha, this is for suppose phase alpha, this is free energy of alpha, okay, and this is how the free energy, the chemical potential can be measured easily graphically. Why is it tangent to curve rule? That also needs to be discussed, that we will discuss later, why it is tangent to curve rules, which tells you the free energy, the chemical potential of the two components at the ends. Now let us, so this is the equation I already showed in the last class, this is basically equation of the straight line. This straight line has equation given by G alpha is equal to 1 minus x mu A plus x mu B. It's obviously this will be all alpha phase, okay, a single phase, that's why you do not write the superscript. Now if I consider multiple phases, what will happen? Suppose this is for okay, this one I have discussed with you, right. Let us apply that, okay. Let us apply these rules for two phases where you have alpha and gamma, okay, and let us consider this is alpha iron solution, this is gamma iron solution in iron and carbon. So this is the alpha free energy curve, G alpha, this is G gamma, okay, right. So now this curve looks like this, again parabolic shape, okay, inverted parabola. So now we can see here that if I want to have chemically potential to you want to have equilibrium, then this must be satisfied. What is that to be satisfied? In that case I have to draw a common tangent between these two curves, the way I have drawn the tangent, and if I draw a common tangent, these points will tell me what? This point will tell me mu A alpha, okay, this point will tell me mu A alpha equal to mu A, because this is A end, this is B end, A beta, because a common tangent. So therefore this curve tangent will tell me mu A alpha phase, this curve tangent will tell me mu A beta phase. So this I satisfy, this condition is satisfied here. Similarly here mu B alpha equal to mu B gamma, sorry this is not beta, this is gamma, here we have drawn gamma, so we have to write down gamma, please make changes. Similar, so therefore these two conditions are satisfied, and this is the way we express or we explain the phase transformations in a classical system. This is the way we explain the phase transformations in a classical system, that the chemical potential of any component A must be equal in all the phases, chemical potential of B must be equal in all the phases. So now let us quickly derive the phase rule, we will get back to you again. If you do not understand, I will again think about it and discuss, but let me just derive whatever time I have in this class, what is the phase rule. Let us suppose I have got C components in a system generalized and P phases in a system, right, alpha, beta, gamma, delta goes up to P. So if I have C component phases, the following things will be satisfied: mu A alpha equal to be mu A beta equal to mu A gamma dot equal to mu A P, because p phases are there. So for a particular component all the phases will satisfy this rule. Similarly mu b alpha equal to mu b beta equal to mu b gamma dot 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 equal to mu b p. P is the number of phase, right. So like that I can write down mu c, there are c components, don't think that's a b c, there are many things, but total number of components c may be any number, maybe 100, 200, 300 possible. So this will become c beta c gamma equal to mu c p, right. So how many equations are there, any idea? Very difficult, right. Let us consider this one. In one row how many equations are there? P minus 1, because one equation is irrelevant. So there are c rows, so therefore total number of equation is c p minus 1. So that means I have total number of equations which are to be satisfied for p component system with p phases, c component p phases is c minus p. But what is the number of variables when I have so many components, so many phases? Number of variables are, let us write down, number of variables are p phases c minus 1 component. Why? That is very simple. If I know the compositions of c minus 1 components, I know composition of all the c components. Why? Because if you have clearly recollect that thing, that xa plus xp plus xc plus xd plus xn equal to 1. So if I know compositions of all the xa, the mole fraction of xa, xp, xc, xn are known, the last one can be easily known because summation is equal to 1. So that is why c minus 1. Now there are p phases, therefore c minus 1 into p is the total number of variables in the system. These are the composition variables. Plus you have temperature and pressure variables. These are the total number of variables. These are the composition variables. Why? Because p is the number of phase and each phase there are c number of components, therefore c minus 1 number of composition variables. Plus temperature and pressure is the two variables. Out of these variables, these ones are fixed by these equations, c minus p, c into p minus 1. This is fixed. This number of variables are already fixed by the thermodynamics. This is what Gibbs has done. Beautiful thing. He could have got Nobel Prize for this, but he died before Nobel Prize started. That's the problem actually. So you can see all this equation must be satisfied. So these are the things which are already fixed by the system. If you do that, what is the number of free variables you get? Free variables are this minus this. This is the total number of variables minus fixed variables. And if you do the math carefully, you will get this, f equal to c minus p plus 2. And this is known as phase rule in the books. Phase rule, this is also known as Gibbs phase rule because Gibbs has derived these equations. Very clearly the number of free variables is equal to number of components minus number of phases plus 2. 2 comes because of we have considered temperature, pressure. You can consider other variables like magnetic field, electric field, then 2 will change. But basically composition pressure variables will be c minus p. Please make sure that in your exam you don't write p minus c, then you will make a mistake. This is c minus p. So therefore number of free variables is equal to c minus p plus 2, and this is what is known as the Gibbs phase rule. Let me also tell you one thing. In metallurgical system we consider pressure to be constant. We have already seen that pressure is always kept 1 atmospheric pressure. So therefore this phase will become c minus p plus 1. This is what is this, because out of 2 variable temperature and pressure, 1 is already constant, so 1 is free, the free is temperature. So composition minus phase plus 1, this is what is the free variables present in a system. I hope this is this very important concept. I told you how to derive phase rule and how to get an idea about different chemical potentials need to satisfy in a particular system. I have already discussed and showed you graphically how we can use it. In the next class actually we will apply this rule. We will see how we can apply this rule, and we will also derive a new rule called lever rule to know the compositions of these phases from the diagrams.